Welcome back to Physics 151 online. We now shift into a part of the course where we will specifically consider the motion of objects that are rotating primarily around a fixed axis. And so some books call this rigid body rotation or rotational dynamics, because we may have an object that's not a point particle, it's extended in size, but it's mounted on some sort of an axle around which it can rotate. And we want to understand, in the first couple of sections of my presentation, the relationship between angular position, angular velocity, and angular acceleration. And then we want to be able to understand the motion of objects that do have this kind of rotational acceleration, where the acceleration is a constant value. Alpha is the symbol that we use for rotational acceleration. So this will serve as an introduction to our next topic. Angular position, velocity, and acceleration. We first have to establish some definitions for how we're going to track the position, velocity, and acceleration of an object that's rotating. And it's just a little bit different than the way we talk about an object that's in a one-dimensional kind of motion. It's analogous to it though, and if we understand the kinematic equations for the motion of a particle in one dimension, we can very easily come up with the corresponding equations for rotational motion. So imagine, like I have here, some object of quite an irregular shape, and it's rotating about an axis that's perpendicular to the page but goes through the origin here, right where those two axes cross. And now let's track the motion of just one piece of the object as it rotates around that axis. And what's interesting is that every piece on this rotating object will make a circular path around the rotation axis, right? So the object itself is not a circle. It doesn't have that kind of symmetry, but every piece of the object will be rotating on a circular path. And so we can very easily relate the position of that piece of the object along the circular path to the radius of its path, the distance it is away from the rotation axis, and the angle that it makes, in this case measured from the positive x-axis. So, angular position, we choose the symbol theta, because rather than a position as a distance, all we have to do to specify the location of this piece is to say what angle it is with respect to the positive x-axis. So theta is the angle, and we call it the angular position. Linear position, which would tell us how far that piece of the object has moved away from the x-axis, would be the arc length s, right? And there's a simple geometrical relation. If you remember your high school geometry, you remember that the arc length of a portion of a circular path is equal to the radius times the angle subtended by that arc. Now this relationship, I will remind you, only holds true if theta is measured in radians. So in this part of the course, if you ever have to use this relationship to do anything computational, remember that theta has to be in radians for that to hold true. So there's a very simple relationship between the linear position and the angular position, and the proportionality is through the radius. The further away a piece of the object is away from the origin, the greater its angular position will be, right? Because it'll be further away the greater its linear position will be, because it'll be further away from the center of the circle. So s gets bigger when you get further away, even though theta stays the same. Now what about velocity? If that piece of the object in its circular path is moving with a speed v, a velocity vector v, we can relate that to the corresponding angular quantity, because v is ds over dt, right? The time rate of change of the linear position. If s is r theta and r is not changing, then the r comes outside of that derivative, and we get r d theta dt. And d theta dt is the time rate of change of the angle. We call that the angular velocity, and we give it the symbol omega, because it tells us the rate of change of the angle with respect to time, just like linear velocity tells us the rate of change of position with respect to time. And notice, this is the Greek letter omega. It's a lowercase omega. It is not w. Please do not call it w. We see with acceleration that there's a very similar kind of relation. Remember that linear acceleration is the time rate of change of velocity. And now if we take v equals r times omega and plug that in here, we take the derivative of that product. R again is a constant. And so we get r times d omega dt, and d omega dt is the time rate of change of angular velocity, which we will call the angular acceleration. And so, for the moment, take a quick look. Position equals radius times angular position. Linear velocity equals radius times angular velocity. Linear acceleration equals radius times angular acceleration. So there's a very simple relationship between all these three quantities. And here, this just makes very clear the identification that I mentioned a few minutes ago. We will call this quantity omega, which is d theta dt, the angular velocity. And we will call alpha, which is d omega dt, we'll call that the angular acceleration. So what we will see in this part of the course is we will derive expressions for many of the same one-dimensional physical quantities that we've encountered in the course so far, but these will all be rotational versions of those same linear quantities. So we've already done this for linear position, velocity, and acceleration, and very shortly we'll be doing the same kind of thing. We'll develop a rotational version of force. It's got a different name. We'll develop a rotational version of mass. It has a different name too. We'll write down a rotational kinetic energy, and then finally we'll come up with an analogous quantity to linear momentum. And I think I've mentioned it already in class. It's called angular momentum. So the analogies, as we go through and derive new expressions for these quantities for rotational motion, remember that they will have a very simple relationship to the formulas that we've already learned for one-dimensional motion. Now, the same way that for one-dimensional motion there was the special case of constant acceleration motion, there often are cases where we have rotational motion with constant angular acceleration. And so we can start with the one-dimensional kinematic equations that were valid for constant acceleration motion and develop one-to-one counterparts for rotational motion with constant angular acceleration. So here's how it works. For a point on a rotating object where it has some initial velocity v0 and then there's some linear acceleration and a time t, this tells us how the velocity of that point changes in time, right? Well, all we have to do to come up with the rotational analog to this equation is replace each of these terms, v, v0, and a, with their rotational counterparts. So here's what happens. V becomes r times omega, v0 becomes r times omega 0, and a becomes r times alpha. And look what happens to that. That factor of r is the same all throughout, so if we divide both sides of the equation by r, we get omega equals omega 0 plus alpha t. And that looks almost identical to the original expression for velocity. So if you remember your one-dimensional kinematic equation for velocity, you should be able to remember this equation for angular velocity. All right? Now, we can do the same kind of thing with all of the other rotational kinematic equations. And I'm not going to work through the derivation, but it's just as simple as this one here for all of those constant acceleration equations. So, just to summarize what the results are, we've already done the first one, right? V equals v0 plus at, that becomes omega equals omega 0 plus alpha t. Now what about this? Instead of x minus x0, we're going to have, for rotational motion, theta minus theta 0. Because remember, we don't measure position in terms of x, we measure it in terms of the angle for rotational motion. v0 becomes omega 0, 1/2 a becomes 1/2 alpha. And so that is the rotational version of this important equation for one-dimensional motion. And once again, we can take the v squared equation and make the appropriate substitutions and cancel out the factor of r, and then we're going to get omega squared minus omega 0 squared is 2 alpha, theta minus theta 0. And the fourth equation that relates the change in theta to omega and omega 0 looks like this. We even had a fifth equation that we wrote down, but I'm not going to reproduce that here. We didn't use it very often. So I'm hoping that you'll see that all you have to really do is remember the one-dimensional equations and then make the appropriate replacements. X for position becomes theta, V becomes omega, A becomes alpha, and these equations are basically expressing the same physics, but now for rotational motion. So there are lots of simple rotational kinematics problems that we can do using these 4 equations. I've given you some on your homework assignment for practice, and we'll do some in class as well. But I hope this has served as a simple but useful introduction to rotational kinematics, and we'll pick this up next time. I'll see you in class.